where we can apply the Fourier series, and we will generalize it for aperiodic signals to get the Fourier transform. Or we can say the Fourier transform is a generalization of Fourier series. All right, so we'll start with the Fourier series representation of continuous time periodic signals. Basically, all signals in time domain, when they are periodic, they can be represented by a summation of linear combination of harmonics or sinusoids. And for generalization, we can say complex sinusoids. And from Euler identity, e to the power j omega equals cosine omega plus j sine omega. And I'll use this j to just for uniformity. And if this one is positive, then that sign is positive. If this one is negative, then this sign is negative. From this formula, we can actually derive two other formulas. So sine of omega equal 1 over 2j e to the power j omega minus e to the power minus j omega. So that's the first expression. The other one is for the cosine equal 1 over 2 e to the power j omega plus e to the power negative j omega. So those are, let's say, we can call them the Euler identity. It starts from this one, and you can derive the other two from there. So the use of complex sinusoids is desirable due to their numerous attractive properties. You know, they are periodic, they go all over, let's say, the time or the wavelength or frequency. They are continuous, differentiable, all these kind of properties are there. So for example, complex sinusoids are continuous and differentiable. They are also easy to integrate and differentiate. Perhaps most important, complex sinusoids are eigenfunctions of LTI systems. Let's not worry about eigenfunctions for now. It's beyond the scope of the course. All right, so an example of Fourier series, for example, this signal could be decomposed. It's a periodic signal because summation of two sinusoids could be decomposed into these two parts. So if you add these two signals, you'll obtain this one there. And also you can go further to create a rectangular wave. Actually, our machines, like function generators, when they create a rectangular waveform, is basically will do a summation of a large number of sinusoids with different frequencies to create this kind of perfectly rectangular waveform. But there is some fluctuations on the peak and at the zero and let's say the zero region here. So basically, it says that this periodic rectangular waveform or pulse wave is nothing but the combination of a lot of sinusoidal waves. For example, this one here, I'm using only 3 sinusoidal terms. So this is the first one, second, and third, and they are weighted with different frequencies. So for this one is sine x, this one sine 3x over 3, this one is sine 5x over 5, and you are getting this output. This is the waveform here. Now, if you add more terms, so up to 13 here, you are getting this, let's say, more into a rectangular shape and with a sharper transition here compared to that one. And the fluctuations are, let's say, magnitude is less than the one before. And this one here up to 13. And if you add more up to 21, you will get even sharper transition and smoother, let's say, peak at the, or less fluctuations on top. So imagine if you have up to 100 or 200 terms, yeah, at some point you will get a perfect rectangular waveform. All right, so how to get this? Okay, we've done this before, the Euler family of identities. And just a recall here, 1 over j equal negative j, and j square is negative 1. So just a refresher here about the complex number j. The reciprocal of j is negative j, and when you square j is negative 1. Okay, all right. So a periodic complex signal x with fundamental period t and fundamental frequency omega naught, which is 2 pi over t, can be represented as a linear combination. So that's the condition. I have a periodic signal. Now, complex is just to have it generalized between real and imaginary. So a periodic complex signal with fundamental period could be represented as a linear combination of harmonically related complex sinusoids. Harmonically related, like different kind of frequencies. So this is the general expression that we'll be using today. So x of t, that's the original signal, equals summation from negative infinity to a certain index k. And I have coefficients, so that's what we call the Fourier coefficients, C of k, or sometimes we call them A of k, it's the same, like here, e to the power j k omega naught t. So all signals, periodic signals, could be represented using this expression. Now this one here, the complex exponent stays at is. The thing that you need to find is this coefficient C of k, and the expression will be described in the next slide. So such a representation is known as the complex exponential form of Fourier series, and C of k, A of k, they are called the Fourier coefficients. All right, so that's what we call a Fourier series tenses equation. So the terms in the summation for k equal k and k equal negative k are called the kth harmonic components. So assume that you have at k equal 5 and another k equal negative 5. So they are harmonically related exponents, harmonic components, basically because they belong to the same sinusoidal signal. Let's take the case at k equal 5, for example. So I have C of 5, e to the power negative j 5 omega naught t. I'm just substituting instead of k, 5. And since it's summation, so this is C of negative 5, sorry, and this is C5, e to the power j 5 omega naught t. And you will find actually C5 and C negative 5, they are equal. So you take them like a common factor, and those are related to the same, whether it was exponent, cosine, or sine. So to denote the signal x of t has a Fourier series. So this one stands for continuous time Fourier series, x of t, c of k. The expression to find c of k is shown here. C of k equal 1 over t. T is the period of the signal. Integration over the period, x of t e to the power minus jk omega naught t. So this is how to find the coefficient ck. Some examples, actually, you don't have to use this expression. For example, here, express x of t sine omega t as a Fourier series term, like find their coefficients. So when the question is express it in the complex Fourier series term, your duty is to find the coefficients ck, because this is the expression here. As I mentioned, those are given. This is the summation. Your task is to find these coefficients. So we'll go back to the question. Sine omega t, we can express it in Fourier term. Sine omega t equal 1 over 2j e to the power j omega t minus e to the power negative j omega t from the Euler identity. Now we can distribute this term. So I have 1 over 2j e to the power j omega t minus 1 over 2j e to the power negative j omega t. Now, if you want to go back to that expression, summation k equal negative infinity to infinity ck e to the power j k omega naught t. If I want to expand this one, I just substitute values of k from negative infinity to infinity. Of course, I will not do that, but we will try from negative 2 to 2 for like these values, because this one you can say c of negative infinity e to the power j k e to the power, okay, I'll use the whiteboard for this. Okay. Discard. So yeah, so x of t equals summation negative infinity to infinity over k ck e to the power j k omega naught t. So this one c of negative infinity e to the power j negative infinity omega naught t plus a lot of terms, then c of negative 2 e to the power j negative 2 omega naught t plus c negative 1 e to the power j negative 1 omega naught t plus c of 0 e to the power j. If you remember, that's how we do summation, right? Omega naught t plus c1 e to the power j 1 omega naught t plus c2 e to the power j 2 omega naught t all the way to infinity. C infinity e to the power j infinity omega naught t. So that's the summation. I just expanded the summation over all values of k. Now, if I want to compare this term to the one that I got for the cosine, which was the sine omega t equals 1 over 2j e to the power j omega t minus 1 over 2j e to the power negative j omega t, right? Now, if you look at these terms, this one here is e to the power negative 2j omega t. This one e to the power negative j omega t. This one c naught alone, because this one e to the power 0. This one c1 e to the power j omega t, c2 e to the power j 2 omega t, and so on. You'll notice that this one has value at, if you want to consider a certain value of k, this one only happens at k equal 1, right? Because if it was 2 omega, like if you want to compare this term with these whole terms here, you will find that only values exist are this one, because this one is e negative j omega t, and this one e j omega t. Omega naught is the same thing. So like here is for the fundamental frequency omega naught, here the fundamental frequency is the same thing, it's omega. So if you want to compare, you will find that I'm having only these two coefficients. All others are, let's say, do not exist in this expression. All right, so if I want to compare this term with this expression, I'll find a match that I have this one here. So I'm getting C1 equals what? 1 over 2j. You want to compare this term to this term. E to the power j omega t, e to the power j omega t, they do exist there. The other one here, c of negative 1 equals negative 1 over 2j. Like this one here. And this one there. And what about all other values for c of k? Will be 0 at k does not equal negative 1 or 1. So if you want to do just like term by term comparison, all other coefficients, they do not exist, only for C1 and C of negative 1. How did I know that? From comparing the exponents. I have e to the power j omega t. I look at this term, I have only this e to the power j omega t. So I will know that C1 will equal this coefficient there. Same thing here for e to the power negative j omega t, e to the power negative j omega t. So I have the same components. That means that I'll have the same coefficients. So C negative 1 equals negative 1 over 2j. And by the way, 2, 1, 3, they're just indices. So C negative 1 is just an index. And that's it. So this is my coefficients. So I can say that my Fourier representation as C1 equal 1 over 2j, C negative 1 over 2j, and all other coefficients for the Fourier series equal to 0, except for k equal -1 and 1. And this is how it is solved in the slides. So let's go back here from current slide. Duplicate. All right, so that's the Euler identity. And by comparing it to the Fourier series, it will have values only at k equal -1 and k equal 1. And here are the values of the coefficients. And it's going to be 0 elsewhere. And by the way, a of -1 or c of -1, in the book we use c, equal -1 over 2j. And we mentioned that 1 over 2j equal -j. So this one is -1 over 2 by -j. We will get 1 over 2j. That's why we're getting it here. So there's no sign difference. It's just j was at the denominator. When I put it up in the denominator, the sign got changed. Is it clear? All right. Okay, so there's the Fourier expression. Another example similar to the one we did before. Okay, so let me just copy it and solve it in the whiteboard. Solution is straightforward. It just requires time, especially when you have a question like this. Okay, copy it. All right, so here for each sinusoid, I will do the Euler identity. So x of t equals 1 is just a constant, so I'll keep it. Plus sine omega naught t, it is 1 over 2j e to the power j omega t minus 1 over 2j e to the power -j omega t. We've done it previously in the previous example. So that's the sine. Cosine. I know the cosine is going to be plus 2 by 1 over 2. The cosine is what? E to the power j omega t plus e to the power -j omega t. That's how the cosine is. From, again, Euler identity. Plus, I have another cosine with double frequency, and there is a phase shift. So 1 over 2, k e to the power j 2 omega t plus pi over 4 plus e to the power -j omega 2 omega t plus pi over 4. Okay. Okay, so we'll just have to do some grouping of similar terms. Like in here, I have j omega t and I have j omega t, so I'll add these coefficients together. Another thing, let's confirm, like this one, -j omega t. No, I think this one has to be minus also, because I'm negating the whole angle. -j 2 pi omega t minus pi over 4, or -j omega 2 omega t plus pi over 4 and distribute. So this one is negative. All right, so let's expand each expression. 1 remains there. 1 plus 1 over 2j e to the power j omega t minus 1 over 2j e to the power -j omega t 1 and 1 will 2 and 2 will cancel. E to the power j omega t plus e to the power negative j omega t plus one thing we will use here, I will e to the power a plus b equals e to the power a times e to the power b, right? Because I have pi over 4. So 1 over 2 e to the power pi over 4 e to the power j 2 omega t. So that's the first expression. E to the power pi over 4, I put it before, the 1/2 still there. And I have e to the power j 2 omega t. Plus, similarly, I'll distribute the half, 1 over 2, e to the power negative pi over 4, e to the power negative j 2 omega t. And from the calculator, you can find the value here for e to the power pi over 4. It could be a certain constant. Okay. There is a mistake. Can somebody correct me? Think about it. There's something missing. Like in here. It's 2 omega naught t plus pi over 4, so? And I hear e to the power j 2 pi omega t plus pi over 4. Why did I multiply this by j, like in here, and this one left it there? Is that correct? You see my point? My point is there should be j and pi over 4 or not? What do you think? Let's consider this term as alpha. Cosine alpha equals 1 over 2 e to the power j alpha plus e to the power negative j alpha. So now let's substitute alpha equals 2 omega naught t plus pi over 4. I will get 1 over 2 e to the power j 2 omega naught t plus pi over 4 plus e to the power negative j 2 omega naught t plus pi over 4. So we realize that there should be a j here. You get it? There should be a j next to the pi over 4. So I will have j and j here. All right. Now let's collect all common terms. Let's start with the most negative exponent. And you'll see why. Like, then you will find that the coefficients will be there automatically. So what is the most negative exponent? This one. So I have 1 over 2 e to the power negative j pi over 4 e to the power negative j 2 omega t. So I'm done with the first term. Then the second next negative exponent, which is the negative 1. I have two terms for the negative 1. I have this expression here, and I have this expression here. So that's for the negative j omega t, negative j omega t. I'm just adding the, let's say, the coefficients. So here we will have plus from this one, 1 minus 1 over 2j e to the power negative j omega t. That's a second negative exponent. I have negative 2. This is negative 1. Then we will have the 0. What is the coefficients for the 0 index? The constant e to the power j0, it's a 1. So I have 1 times e to the power j omega 0. So that's plus 1 plus the first positive component here, j omega t, and this one here. So I'll have 1 plus 1 over 2j e to the power j omega t. And the last coefficients will be this term here, plus 1 over 2 e to the power j pi over 4 e to the power j 2 omega t. All right, so what's next is to find the coefficients. Now, by looking at the exponents, you'll find this term is c of -2. This is c of -1. This is c of 0, c of 1, c of 2. Why? This is j2 omega t. If you go back to the Fourier series, ck e to the power j k 2 omega t, and k equal -infinity to infinity. So we'll start with the first expression. What is the value of k to make this expression like this? It's -2. So that's c of -2. Then this is c of -1, c of 0, c of 1, and c of 2. And that's it. And you can confirm here the solution. Okay, they expanded the e to the power j over pi over 4. There is no need to do that. But a of 0 is 1. That's what we obtained here. That's a of 0. And we will have a of 1, 1 plus 1 over 2j. 1 plus 1 over 2j. C1, A1 is the same as I mentioned before. A of 2, which is 1/2 e to the power j pi over 4. This term here. A of -1, that's a of -1. 1 minus 1 over 2j, 1 minus 1 over 2j, and the last part of -2, 1/2 over times e to the power -j pi over 4, this one here. So those are the coefficients. And you still have to mention that at c of k equals 0, at k does not equal -2, -1, 0, 1, 2. Like if k is not one of these values, then the coefficient will be 0. And that's another representation for that. Is it clear how to find the coefficients from a sinusoid you'll be given? That's a common question you'll find either in the second quiz or the final. The second quiz, I think it's too early to talk about it. It's going to be a few weeks from now. All right. Slideshow from current slide. 2 weeks from now or 3. We have plenty of time. All righty. This example here is a bit different. Find the coefficient C of k for this expression. So there's no expression actually. It's a rectangular waveform. So this periodic square wave sketched in this figure below and defined over this one period. It has a value of 1 from -t1 to t1 and 0 elsewhere. So it's a signal that will encounter a number of times, whatever. To determine the Fourier series coefficients, you apply that expression here. C of k equal 1 over t, integration over the period, x of t e to the power -j omega dot t. And you just substitute 1 here. And my period is at t1. So 1 over t1, t1. Solve, you will get this answer here. A of k or C of k, the coefficient is sine k omega naught t, 1 over k pi. So how it was obtained? As I mentioned, the terms of the integration will be from t1, -t1 to t1, because that's my signal is 0 elsewhere. That's 0 here and 0 here, and I'm integrating over one period only. So I don't have to do the integration for the whole series. So over one period. So it's going to be from -t over 2 to t over 2. But I have zero values from t1 to t over 2 and negative t over 2 to negative t1. So they will cancel, and my integration will be from negative t1 to t1. So we'll go back to the integration. So it's going to be 1 over t1. That's my period. And the amplitude here for the function, it's 1, as it was also defined here. And that's it. You have integration of exponent. Then 1 over t, you have 1 over negative j k omega naught. And I have the exponential integration for exponent. And I have the limits t1 and negative t1. Just substitute the values. And you will end up with this expression. And using Euler identity backwards, you have two exponents, difference between them, so that will lead to a sign. So these two terms here will lead to the sine function. Then you will have 2 sine k omega naught t1 over k omega naught t. And you can substitute t equals, omega naught is 2 pi over t. So they will cancel each other, and that's the final expression. So sine k omega naught t1 over k pi, and that's what we call a sinc function. All right. So that's it for the Fourier series. It just restricted for periodic signals, and the task is to find the coefficients. There are two ways. There is, like usually, the question will be given in terms of sinusoids. You decompose each sinusoid into its Euler identity, then group similar terms together, and from there you'll find the coefficients. Another example like this one, you have the function, use the formula to find the coefficients of that function. All right, now to generalize it, go beyond periodic signals, we'll use something called the Fourier transform. And I believe that's something you have done in advanced math before, Fourier transform. And the series, you've done in the series before, and how to take the coefficients, like these two examples. Have you done something before in advanced math or no? What was the way? A bit different. It doesn't matter. That way?
No, we used to take it with used to take us like a whole page to go through.
Yeah, it's something like this. You have to apply the formula, and you will have integration, yes, probably by parts, by substitution, etc., etc. Yeah, and that's why it will take long. Yeah, like this one here, because the amplitude is 1, so the integration was easy. But imagine the amplitude was sine. You have sine times exponential. You have to do integration by parts twice, then etc., etc. All right. Now let's do you've done Fourier transform. So what is the task for Fourier transform? Why do you need to use Fourier analysis in general? Any idea? Basically, signals in time domain, that's what we see in real life. That's what we deal with. However, there are some information that we cannot see in time domain, like the frequency component. So for example, the human speech, you can talk all day long. However, the range of frequencies, you cannot speak louder or at a frequency range that is higher than 4 kilohertz. That's a human speech. So you can get most of the information in a wavelength between, or a frequency range between 300 hertz to 4 kilohertz. And so you can do some analysis in that range of frequencies. So there are more information, or different kind of information can be seen in the Fourier domain that you cannot see it in the time domain. And you can do things like filtering, denoising, etc. A lot of things could be done at the frequency domain, or it will have more, let's say, understanding about the information you have that you cannot see in time domain. All right. So the Fourier transform, simple formula, it's integration from negative infinity to infinity, x of t, that's the function of time, times e to the power negative j omega t. And that's it. The inverse is similar, but you'll have a positive exponent, and you divide over 2 pi. So that's the forward Fourier transform. You go from time domain into frequency domain. So here you integrate with respect to t. The inverse Fourier transform, you go from wavelength or frequency into time. And your integration will be in terms of omega. And there's another expression here also, x of t equal integration from minus infinity to infinity, x of f e to the power j 2 pi f df. Like if you have the signal represented in frequency domain in f. We'll stick with the book. So we'll be dealing with omega most of our analysis. Okay, so they are Fourier pairs, and yeah, you'll see now that we'll be rely a lot on tables using the pairs. So let's see this as an example. Consider the signal x of t e to the power negative at u of t, and find the Fourier transform. So let's do it simply on the whiteboard. Okay, x of t equal e to the power minus at u of t. So x of omega equal integration from minus infinity to infinity e to the power minus at u of t e to the power minus j omega t dot dt. We know that the unit step function has one task, and that task is what? To have the integration starts from 0. Because my unit step function starts from 0, and it's 0 when you have t less than 0. So the integration below this point will always lead to 0. Then my integration will become integration from 0 to infinity e to the power minus at e minus j omega t dot dt. All right, so we can take t as a common factor here, and I will have integration from 0 to infinity e to the power, I will have t there. So here I'll have negative a minus j omega dot dt. And that will lead to what? 1 over negative a minus j omega from 0 to infinity e to the power negative a plus j omega t. All right, so we can substitute. So the first one will be 1 minus a minus j omega e to the power minus a minus j omega times infinity, and minus 1 over negative a minus j omega e to the power minus a minus j omega 0, right? All right, so this exponent, what will be the answer? Someone might think it is going to be infinity because I have infinity, but if you take a plus j omega as a common factor, and I'll have negative infinity, so that will lead to 0. And this one will obviously lead to 1. So I will have this term 0 minus 1 over negative a minus j omega. And again, I'll take the negative sign as a common factor. So I will get 1 over a plus j omega. And that's the final answer here. And I believe we are getting the same thing. All right, so you can take it as a rule that the first Fourier pair e to the power minus at, and a should be positive, by the way. The Fourier transform 1 over a plus j omega. That's the first Fourier pair. Now, usually Fourier numbers are complex, so they come in the form with magnitude and phase. So how to find the magnitude for this expression? Let's say x of omega could be represented by the amplitude or magnitude x of omega times e to the power phase of x of omega. So how to find the magnitude for this one? Magnitude could be expressed easily as a square root of z times z conjugate. So what is the conjugate of this? You know what conjugate is? You heard of the word conjugate?
Yeah.
So what is the conjugate of this one? 1 over a minus j. So x of omega equals 1 over a plus j omega. Sorry. Times 1 over a minus j omega under the square root. So it's going to be 1 over a square minus omega square. That's the magnitude. Let's confirm. And a square plus, well, that will be different of 2 squares. And yeah, you can say that square root of a over square root of b equals square root of a over b. Since I have 1 here, so it's going to be 1 over. But both are the same answer. You just want to stick with the reference we have there. So that's the magnitude. What about the phase? So for the phase of x of omega, salam equals what? Tan inverse of imaginary part of x of omega over the real part of x of omega. So x of omega equal 1 over a plus j omega. How to find the real part and the imaginary part? A simple way is to multiply by the conjugate of the numerator. You multiply by 1a minus j omega over a minus j omega. So the reason is I'm multiplying by 1. That's the first thing. So this is like multiplication by 1, no difference to the amplitude. The thing is my complex numbers will be in the numerator. It will be easier to deal with. I can easily separate them. So that will lead to a minus j omega over a square plus omega square. So the real part of x of omega will equal a over a square plus omega square. The imaginary part of x of omega equal negative j omega over a square plus omega square. However, since I said this is the imaginary part, there is no need to put the j. J is just because each number is considered as represented like this. So the imaginary, there's no need to put the j. All right, so the phase will be tan inverse of negative omega over omega square plus a square over a over omega a square plus omega square. They will cancel, so tan inverse of negative omega over a. That will be the phase for this expression. Okay, that's not solved. No, not solved. But yeah, the continuation is, so this is the real and imaginary part. Take the tan inverse, numerator and denominator will denominator for both expressions will cancel. I'll have negative a over negative omega over a. That will be the phase. All right. So that's it for this example. In the exam, I may ask you the like all requirements: find the Fourier transform, find the magnitude, and find the phase. Let's see another example. Consider this rectangular pulse. X of t equal 1 from negative t1 to t1. If you recall, absolute value of t less than t1, that means that the values of t is from negative t1 to t1. And this is how you represent this expression, or how you plot this expression. Similarly, we can apply the Fourier transform for this. So x of t equal 1, absolute value of t less than t1, and 0 elsewhere. To plot it, so just a rectangular pulse, and this is 0, this is t1, negative t1, and the amplitude is 1, and this is the time axis. So x of omega equal integration from negative infinity to infinity x of t e to the power negative j omega t dot dt, and that equals integration. Since I have zeros beyond t negative t1 and t1, so my integration from negative t1 to t1, amplitude is 1 e to the power negative j omega t dot t. السلام ورحمة الله عليه. All right, so let's do the integration here. It's going to be negative 1 over j omega e to the power negative j omega t from negative t1 to t1. All right, so substitute. I have negative 1 over j omega. By the way, it's 1 over negative j omega, but I put it in top. Okay, times e to the power negative j omega t1 minus e to the power, okay, negative by negative j omega t1. If you look at this value, what do you think will be the proper expression for this? Is it sine or cosine? Cosine plus. When you see when you say the plus sign between two exponents, cosine will be a better candidate, but there's a difference here, so that's a sine. Now, but in the sine, we are used to see e to the power j omega minus e to the power negative j omega. Here I have the opposite, e to the power negative j omega minus e to the power j omega. So that's minus sign. So this will lead to minus sine of omega t1. But we are not done yet. We know from Euler identity that what sine omega e to the power j omega minus e power minus j omega divides by what? 2j. So I'm having this expression only. So that's going to be sine omega times 2j. So agree with me on this one? So we multiply by 2j, and let's not forget our initial expression, j omega. Negative 1 over j omega times this. So this one will go down there, and this expression is negative sine omega t1 times 2j. All right, so j and j will cancel. Negative and negative will go. So I will have 2 sine 2j, okay, 2 sine omega t1 over omega. And that's it. Omega t1, omega, yeah. Let's confirm our solution here. You will get 2 over omega sine omega t1. 2 over omega sine omega t1. All right, so to convert it to a function that we know, we multiply by t1 by t1, and we will get 2 t1 sine omega t1 over omega t1. This one, just to say that this is what we call a sinc function, sinc omega t1. Sinc x equals sine x over x. All right, so that is the final answer, but to me that is enough. Like, you reach this point, that should be more than enough. Okay, so that's the sinc. All right, so let's go into the Fourier pairs. We've seen that this rectangular waveform here led to a sinc function. We've seen the exponent led to 1 over a plus j omega, and so on and so on. So that's the representation of this rectangular waveform. By doing continuous time Fourier transform, you are getting a sinc. And let's see, here are some tables. By the way, tables will be provided during the exam, so you don't need to memorize it, but it's better to understand. So those are some properties. Linearity, that when you have two functions, x1 and x2, are weighted and added, their Fourier transform is simply the individual Fourier transform for each multiplied by the same coefficient, and they are just added. When you do shifting in time domain, so by a certain shift t naught, that will lead to a multiplication by an exponent in frequency domain, e to the power minus j omega naught t. We'll see an example about this one in a few minutes. When you do shifting in frequency domain, that's what we call frequency domain shifting. And scaling, conjugation, but this is the important one to me. That's the one. There is a principle we call duality principle. Let's say, for example, here, the rectangular waveform in time domain led to a sinc waveform in frequency domain. So if I have a sinc waveform in time domain, it will lead to a rectangular waveform in frequency domain. That's what we mean by duality principle. Like, that's what, like, Fourier pairs are. So that's the duality x of t. So here you have it as a Fourier transform. You will have the function here. Convolution. You've seen like how convolution like need a lot of work in time domain. Doing it in frequency domain is easy. You just multiply the Fourier transform for each function. Okay, derivatives. Things we'll do inshallah next week. Actually, we'll give them more time. When you take the derivative in time domain, you multiply by j omega in frequency domain. So basically, to put it as a rule here, dn over dt n of x of t, it means that the nth derivative, by doing Fourier transform, you'll get j omega to the power n x of omega. So when you take the first derivative, you multiply by j omega. You multiply, when you have the second derivative, you multiply by j omega square, which is negative omega square. When you get the third derivative, you multiply by j omega cube, and so on. Because this one will help us in solving differential equations. All right. Fourier pairs, the impulse function in time domain, delta t, will lead to 1 in frequency domain. The unit step function will get to pi omega delta of omega plus j 1 over j omega. By the way, those things are, let's say, could not be easily solved by using just like the straightforward formula. There is a lot of let's say numerical solutions to solve them. Using the duality principle, I have 1 in time domain, it will lead to a delta in frequency domain. So there you go. I have 1 I have delta in time domain, it led to 1. I have 1 in time domain, it led to a delta in frequency domain. The shifting, sine, and cosine, they have their own transformations. Direct function will lead to a sinc, and sinc will lead to a rect, and so on. Okay, another set of pairs. Yeah, will not rely to a lot. Like there is some repetition, like this one here. All for those three here were already mentioned here. That's the delta there, and the sinusoidals. So there's a repetition here. Like each book has its own table of Fourier pairs. It depends on the author. All right. This one is just to show that when you have a delta function in time domain, the Fourier transform will be number 1 for all frequencies. Like this. So this is delta in time domain, and that's the Fourier transform. So it's a value of 1 over all the whole range of frequencies. The sinc function will lead to a rect. Now, when you expand the sinc, the rect function will shrink. So when you expand in time domain, frequency domain will shrink, and the opposite. When you shrink in time domain, frequency domain will expand. So this one here, you have a sinc function in time domain. That is corresponding rect function. Now this function a little bit expanded when compared to the previous one. It shrunk in frequency domain. Expanded more shrinking in the frequency domain, and so on. All right, so here are some properties. I think we already discussed that. Translation in time will lead to a multiplication shift. Why do we need this to solve this example? So assume that you have this Fourier transform, and you were asked to find you were given the energy. Now wait a minute. This is the example, yeah. Yeah, that's the example I wanted. Yeah, this one. So find the Fourier transform for the signal given below. So you have a signal from 1 to 4 has value equal 1 from 1 to 2 and 3 to 4, and have a value 1.45 from 2 to 3. So it's none of the standard functions we have seen here. However, if you look at it, it looks like what? Rectangles. Like you can say that these are rectangles that have been added together. Copy. Control V, paste. So you can say that this is the addition of these two rectangles. I have a rectangle from 1 to 4 has a value of 1, plus another rectangle from where to where, 2 to 3, and the amplitude is 0.5. So like when you just add these two rectangles, the result will lead something. So that equals this. Like when you add this to this, you will get a similar shape to this. So once you have it like this, the answer should be, or the solution should be something clear. I have two rectangles and they are added, and I want to apply the Fourier transform. And from the linearity property, we said that ax1 of t plus bx2 of t, by doing Fourier pair transforms, I will get ax of omega x1 plus b x2 of omega. So I need to find the transform for this, find the transform for this, and that's it. Add them together. All right, so the first one, what will be the proper presentation or representation of it? So it's a rectangle. Let's go back to the tables. And the tables, we have the issue that each rectangle is centered as 0. like here, like this example where, yeah, like this rectangle is centered as 0. So I'll get a sink, but this is not my standard rectangle. This is a shifted rectangle. So this rectangle, if I wanted to center it as 0, what will be the values of those? How much is the length? 3. So this one is basically a rectangle. The length is 3. So if I want to center it as 0, what will be these two values? Okay, length is 3 divided by half. 1.5 to 1.5. Negative 1.5 to 1.5. How about this one? 0.5 negative to 0.5 positive. Okay, if I want to represent them arithmetically or mathematically, if you remember, rect of t over t. We've done the rectangular waveform at the signals part. It was what? 1 absolute value of t less than t over 2 and 0 elsewhere. So this one is rect t over 3 and this is rect t. So if you remember this rectangular, the rect function, rect t over tau or rect over t over uppercase t, then it will have values from negative t over 2 to t over 2, uppercase t over 2 over uppercase 2 over uppercase t over 2. All right, then this function has been shifted to the right by how much? I was 1.5, it became 4, then I shifted by how much? So this is rect t over 3, 2.5. Why? 1.5 plus 2.5, that is 4. And I have minus y because shifting to the right. Similar thing here, it's rect t, how much? Same thing, 2.5 minus 2.5. So I have shifting by t naught equal 2.5 for both. So here I have rectangles and I have shifting. So let's see what will be the solution. First, we'll start with the standard rect for this one. What will be the Fourier transform for this? So let's go to the tables. Let's look for the rect. There you go. That's the expression that I want. Rect t over uppercase t. It will lead to absolute value of t, sinc t omega over 2. What is the value of t? For the first one, it is 3. The second one is 1 because I have two Fourier transform. So let's solve each one individually and put it in the side and then add them together. So let's solve for x1. So x1 of omega is basically the Fourier transform of x1 of t. I'll start with this. x1 of t equals rect of t over 3. Then x1 of omega equals what? Absolute value of 3, sinc 3 omega over 2. 3 omega over 2. So that's the standard rect. Now, after shifting, now I have time shift by how much? 2.5. Let's look for the shifted property. And I have where time domain shifting. x of t minus t naught. I shifted by 2.5, then I multiply my transformation by e to the power negative j omega 2.5, which is t naught. So after shifting, I will get 3 e to the power negative j omega 2.5, then multiply by the sink. Sink 3 omega over 2. So that's it. That's the first expression. I started from the standard rectangle, found the transform, then I apply the time domain shifting, which is the scaling in the frequency domain by e to the power j omega by the amount of that shift, which is 2.5. And that's it. That's the first expression. Now, what about x1? So x1 of t, standard here, rect of t. That's before shifting. Let's do before shifting. Now, what is the value of uppercase t? It's 1. So in this case, x1 of omega will be what? 1 absolute value by sink 1 times omega over 2, which is sink omega over 2. Now, apply the shifting after shifting. You will get what? 1 times e to the power minus j omega 2.5, because the same amount of shift, sink omega over 2. And that's it. Now the final answer will be the addition of both. So x of omega equal. Let's take the e to the power negative j omega naught, j omega 2.5 as a common factor. So e to the power negative j omega 2.5, 3 sink 3 omega over 2 plus sink omega over 2. And that is the final answer. Let's confirm. E to the power negative j 5 over 2, which is 2.5. 2 sine. Okay, so it was solved in terms of sine, but we did it with the terms of sink, so it should be the same answer. Alrighty. Sine omega over 2, 2 sink. Okay, which is 1. Okay, that's it. All right, there is one of the theories. It's called Parseval theory. Parseval is more related into energy. So it says that the energy in time domain, or the energy of the signal in time domain, equals the energy of the signal in frequency domain. And that's it. So the energy expression in time domain is summation over all period of time from negative infinity to infinity, x of t squared, absolute value, or the magnitude squared, dt. And that's equivalent to taking the integration for the Fourier transform that you divide over 2 pi. And that's it. That's the Parseval relation. So they're kind of the same expression, except for you have the 2 pi factor. So if you are provided such an example for this given Fourier transform, find the energy. All you need to do is find the magnitude, then square each component, do the addition, and scale by 2 pi. So in this one here, you can easily divide this summation into 3 intervals. This is the first one. This is the second one. So I have this and this and this. So let's take it there to the slides, or to the whiteboard, sorry. So we know, since it's given in frequency domain, you have to do the energy of x equal integration from negative infinity to infinity, x of omega amplitude, in case we have, let's say, complex values, squared dot d omega. An important part here is what they call it is to scale over 2 pi. All right, then that will equal 1 over 2 pi. Take it as a common factor, and I will have the integration from -1 to -5 plus integration from -0.5 to 0.5 plus the integration from 0.5 to 1. All right, so simply 1 over 2 pi. The integration, what is the first value here? Negative square root, square root of pi. So square root of pi squared plus integration square root of pi over 2 squared plus square root of pi also squared. Since we have real values, what is the physical meaning of integration? What is integration? Find the area, exactly. And since we have real values, so I'm finding areas of rectangles. So here it's a rectangle. What's the length? Half. So in this case, 1 over 2 pi, 0.5 times pi plus, what is the length here? That's 1 times pi over 2 plus, similar thing here, 0.5 times pi. Length, so I'm taking physical values, so there should be positive values. Don't say, oh, the distance is negative 0.5 and you put -1. No, the length is here 0.5 times this amplitude squared here. So in this case, I will get 1 over 2 pi plus pi over 2 plus pi. And in this case, 1 over 2 pi, 5 pi over 2. Pi and pi will be gone, will be 5 over 4 over 8 or over 4. Square root of pi over 2. So the 2 is not, I copied it incorrectly. So just square root of pi there, square root of pi there. So 2 is not. So I have 4. Then it's 5 pi over 4. And in that case, it's not 5 pi over 4, it's something different. This one is pi over 2, pi over 2. Okay, yeah, 5 pi over 4, 5 over 8. Yeah, my mistake here, I thought the square root is for the whole expression. So I just follow the square root of pi, not 2. All right. So that is Parseval theorem. Okay, slideshow from current slide. Okay. All right. One of the important things here you will see it in future with, let's say, in many systems. All systems are modeled like this. So I have my input x of t. I have my system. I think we've done that, h of t, and I have my output y of t. And we've seen in time domain y of t is basically x of t convolved with h of t. I think we've done it in discrete domain with h of n, but it's the same thing for continuous domain. You have a system and you have an input signal or excitation signal. The relationship between them is convolution. So y of t equals x of t convolved with h of t. Now in frequency domain, if I want to represent everything in frequency domain, which is easier, so the same block diagram, x of omega, h of omega. By the way, in frequency domain, we represent everything in uppercase. That will lead to y omega. So the relationship y of omega equal x of omega times h of omega. Dealing with the multiplication is way easier than dealing with convolution. So that's one of the properties here. Now, usually we want to find the system response. So usually what happens in labs, you control the input and you observe the output. So you have the input and you have the output. Now you want to find the response of the system. So since we are dealing with Fourier transform or Fourier analysis, the response of the system h of omega is simply y of omega over h of omega. Sorry, x of omega. H of omega, the response, system response, equals the output response over the input response, y of omega over x of omega. Now, once you have h of omega, then you can find what? H of t, something we call the impulse response. So this one is the frequency response, that's the impulse response. We'll talk about it later. And that's it. Once you have this information, you have full control of your system, that you know how to, let's say, the behavior of the system. And that's what we call the system is completely characterized. I have the expression of that system. All right. So in general case, the frequency response H usually is complex valued, but most of the time we have it in real valued. However, we are represented in terms of magnitude and phase. Okay, so yeah, magnitude phase, something quite simple. So the magnitude of the system Y equals the magnitude of the input X times the magnitude of the input H, because I'm having multiplication relationship. Now in phases, we don't do multiplication, we what do you call it? We add the angles or we add the phases, simply because each expression here, Y of omega equals the amplitude of omega times e to the power the phase of omega. That equal the amplitude of x times e to the power phase of x. That's times the amplitude of h times e to the power the phase of h. So if you want to find the magnitude of y, that will be the magnitude of those. Now, when you have multiplication of exponents, that will lead to e to the power phase of x plus phase of h, and that will be phase of y. So that's why the phases will be added, but amplitudes or magnitudes will be multiplied. Is it clear? I'm not going to ask you how to derive it, but keep that in your mind. All right, so we have the system here. Okay, many LTI practice interest can be represented. Yeah, let's continue next week. Engineer Haitham just informed me that he has something to do later today, so he wants you to be in the lab early. So please go immediately to the lab, and this will continue, inshallah, next week. All right, so let's stop sharing.